In this video, I want to discuss rules of exponents. So you've hopefully learned by now that when I put a little number up here, it's a abbreviation, nothing more, for repeated multiplication. Whether I have a letter or a number, okay, it's still just repeated multiplications, nothing but an abbreviation. So I want you to think about that there's no deep, brilliant, complex idea involving exponents, so that when I show you these rules, again, there's no brilliant thing underneath the hood. Okay, if you pull back the curtain, it's just an abbreviation. Okay, in fact, if you ever get confused by anything I'm going to say, what I'd like you to do is write it out. Say, what is this an abbreviation for? And then by thinking along those lines, you could make anything that's unclear obvious. All right, so let's first, what I'm going to do is I'm going to talk about patterns that happen to be true whenever you have products, quotients, and levels of exponents. Okay, those are the three things I'm going to hit in this video. So for example, if I had 3 squared times 3 to the 4, that's going to turn out to be 3 to the 6. If I had 13 to the 5 times 13 to the 10, that's going to turn out to be 13 to the 15. So the big idea here is that when you have any number to, let's say, the a power times the same number to the b power, it's a plus b. So the point is that you add the exponents. Okay, now if you think about that, you might be able to see why that has to be true. Okay, let me write out the 3's and you will see why that has to be true. So ask yourself, the 3 squared, how many 3's does that have? That has 2, right? And how many 3's does the 4 exponent entail? That entails 4. So now you count them all up. How many do you have? Well, you have 2 plus 4. See that? So each exponent, or the exponent tells you how many are multiplied together, so you add those. That's the total number that are multiplied together. All right. Likewise, with the 13's, you have 5 13's, and then the other one would give you 10 13's. Okay, so 5 and 10, so clearly the total is 15. All right, so that's the product rule of exponents. Okay, now let's do the quotient rule. So now let's first take an aside for a second. Do you know that if you have a fraction that's composed of products, so like 5 times 4 on top and 5 times 3 on bottom, okay, do you know that when you have a common factor on the top and bottom, you can just eliminate it? Okay, so people say that they cancel it out. All right, so keep that idea in the forefront of your mind when you try to understand the quotient rule. All right, so we want to now ask ourselves, if I have like 7 to the 10 divided by 7 to the 3, okay, why does that reduce to 7 to the 4? If I have 8 to the 9 divided by 8 to the 2, why does that reduce to 8 to the 7? All right, now putting it all together, the big idea is that if you have a number to the exponent a divided by a number to the exponent b, you get a minus b. So if you notice both purple examples, you're subtracting the, oh, by the way, I'm sorry, the very first example should have been 10 to the 7. Okay, so sorry about that. All right, so the 7 to the 10 and 7 to the 3 equals 7 to the 10 minus 3. And then on the bottom, 8 to the 9 divided by 8 to the 2 gives 8 to the 9 minus 2. All right, and so again, the big idea is that you subtract the exponents. All right, now think about why that is true. All right, let's do the sevens as an example. So what does the 7 to the 10 mean? I'll do it in the bottom left. That means I've got 10 sevens, for crying out loud, on top. And on bottom I've got 3. All right, if you can imagine yourself writing it out that way, using the cancellation thing that we were talking about initially, you would probably see that you could cancel 3 on top with 3 on bottom, right? Now ask yourself, how many do you have left on top? Well, we start out with 10 and we took away 3, so we have 10 minus 3 left. See that? Let's do the eights example. So again, we have 9 eighths on top and we have 2 on bottom, so you could see that you would cancel out 2. So you're always subtracting, right? You're losing numbers on top, and so therefore the exponent is going to get smaller. You subtract. That's how you get the quotient rule. All right. Now, in a future video, we'll talk about what happens if you have a bigger number on bottom. Okay, but we're not there yet. Okay, and then the last rule I want to talk about: what happens if you have like 5 squared to the and that whole mess is raised to the third. Okay, why does that equal 5 to the 6? And then if you have 2 to the 4 to the 5, why does that equal 2 to the 20? All right, the pattern here that we're trying to figure out why it's true is if you have any number to an exponent and that whole power is raised to another exponent, you get x to the single exponent, which is the product. Okay, let's work that out. Okay, so let's do the first one. So 5 squared cubed. So that, what does that mean? That means that we've got 3 5 squared, right? Okay, well what does each 5 squared mean? Each 5 squared means that you have 2 5s multiplied together. All right, so then ask yourself, so how many 5s total do we have? Well, we have, count them, 2 times 3, so that gives 6. Okay, the same idea will work with any number. So like the 2 to the 4 to the 5, so we've got 5 2 to the 4s, right? Each of those is a packet of 4, so you would have 2 times 2 times 2 times 2, and then you'd have 5 of those quartets, to use a fancy word. So count them all, 5 times 4, so that means you would have 20. All right, that's why that one works. Okay, now I'm going to finish with a related rule that you might call distributing exponents, but if you understand these, you will, and you understand how I was able to work it out to derive the 3 formulas, you should see right away why these have to be true. All right, if I have something times something else to a power, that's the same as if I quote-unquote distributed the exponent. Okay, I'll leave it as an exercise for you to do the following. Do 3 times 4 to the 5 and then work it out, and you'll see that you have 5 3s and 5 4s, and so you always have the same number of each, and so it should be clear why this rule holds. Also, if I had a quotient divided by the whole quotient raised to an exponent, that's the same as if I had the exponent on the numerator and the denominator. Let me fix up my denominator here just a second. Okay, and I'll leave it as an exercise again for you to work it out the same way I did the other ones. Think about if I had 3/4 to the, let's say the 3, so that would mean that you have 3/4 multiplied together. So then ask yourself how many 3s you have on top and bottom, and you'll see that it's the same. Okay, and that'll explain that one. So these are the final 2 that are kind of related to the other 3 that I gave you that you need to know.